Ah, welcome, my intrepid explorer, to the grand finale of Week 1, or as some might call it, Day 4. I must confess, you've performed surprisingly well. For a human, that is. Today, we're going to add a touch more complexity and a dash more brilliance to your drowning nightlight. We're fixing the storage room and cockpit lights so you won't have to grope around like a lost mole rat any longer. We're still under an ocean. You're getting cold, and the night is dark and full of scampi. We've a problem. Yes, another one. The hydroponic system that filters your breathable atmosphere needs more light to photosynthesize, soak up your bad breath, and turn it into O2. We need to get the rest of these dip switch circuits operating before whatever's out there starts looking at us like a can of spaghetti. First things first, the hardware. Notice how we've added a couple of LEDs and some extra wires for our dip switch? Don't start flipping switches just yet, though. Without proper instructions in your code, they'll just stare back at you with the cold, lifeless gaze of purposeless tech. And that brings us to our code, our all-important guide to technological obedience. We're defining 6 new variables that will tell us which pins are pulling their weight in the circuit. In the setup function, we'll use the pin mode function to designate switches as inputs and LEDs as outputs. Finally, we'll march into the loop function and create 3 if statements, our conditional knights in shining armor. They'll relay the status of the 3 dip switches. So, my brave explorer, are you ready to turn our ship bright enough to lure all manner of prey and predators in this unexplored ocean? I know, I'm excited too. Once you've finished wiring, upload your new code to the hero and let there be light. You know the drill. Let's turn to some instructional material I was able to gather cached on the computer. And you guessed it, I've also added this to your mission resources for future reference. I'll see you soon.
Hello and welcome back to Day 4 of the 30 Days Lost in Space Adventure Kit. Yesterday we were able to successfully connect one of our lights to an LED using the dip switch module. However, we still have, it seems, 2 more lights within the ship that need to be controlled with on and off in order to fully fix all the lighting in our spacecraft. So today we're going to be taking what we did yesterday and we're just going to be adding on additional logic for the additional lights that we had from yesterday. Most of the logic that we have is pretty similar to what we have done in previous days from yesterday. We're just kind of doing it for a couple more pins and a couple more LED outputs. So that's all we're going to do today. Starting off, let's do what we normally do. We have all these comments. If they're daunting, you can feel free to close them down and you don't have to look at them. Now, you'll notice that there's one other thing that we've done as well if we scroll down to where we usually define our pinouts. Today I'm going to be showing you another way to do the exact same thing, and this is the way that we're going to be doing it going forward. In the past, in previous days, we used a pound define statement to share what pins we are going to be using for our inputs and outputs at the top of our code. This is a good way to do it. This is the way that a lot of code has been using it for a lot of time at this point. However, the way that that is done is currently depreciated in the Arduino IDE, in the Arduino programming language. What this means, depreciation in code, means that it is currently not best practice to continue using it. It means that they're no longer going to be supporting that method of doing something. And in this case, the pound define has been depreciated. It still works. It doesn't seem like it will break in any time, shape, or form in a long, long time. However, if you hover over type alias byte, which is a uint underscore 8t type, you can define the pins using a constant, meaning it's not going to change, byte, which is a data type of type uint 8 underscore t, and we can say that this is going to be 10. So here's the old way of doing it, and here's the way that we're going to be doing it going forward. If you still want to do pound defines, you can, and it will work. However, for good programming sake, we're going to be using the non-depreciated method, which is going to be using bytes, which is of type uint8 underscore t. You're wondering what the heck that is. Don't worry too much about it. It's simply a data type of what you would think would be 8 bits. And the reason why we want to use a byte of this is because if you go to pin mode and you go into this function here and you hover over it, you'll see that the input it wants is of type uint8 underscore t pin and uint8 underscore t mode. What that means is we're simply just giving this function when it calls it what it wants. So there's no confusion with the compiler. It doesn't have to do any unnecessary conversions and etc. So if you use define, I believe it does the exact same thing and there should be no issues, but just for depreciation's sake, we're going to be going forward. And so if you see const byte and then whatever pin we're defining up at the top of our code in future videos, you can think of it as the exact same thing functionality-wise as doing a pound define statement. Now with that out of the way, let's make sure that we close all these extra comment blocks just to make sure that there's no additional confusion. We also have at the top the included libraries if you're using the Arduino IDE and you just accidentally happen to erase that. Nothing will change as the Arduino IDE automatically adds that anyway. But it's good just to have it anyway so you know that it's being added automatically. If we go down here, we can go to our very first line of code, and the very first bit of code that we have is defining our pinouts. Now, instead of using the pound define, we're going to be doing const byte cabin lights pin is equal to 10, and now we have 2 additional ones for each of the extra 2 lights. We have the lights for our storage bay and our cockpit lights. So, we have constant. Constant simply means that it is exactly that. It is constant. It will not change. If you try to change this variable, let's just say you go down to the loop and you want to write something like storage lights pin equals storage lights pin plus 1, and you want to add 1 to it, essentially trying to make it 12 or whatever. This constant will throw out an error and it will say, hey, buddy, you can't do that. It's a constant. It's got to stay the same. By putting constant, it just enforces and makes sure that this is not going to change, and we don't want it to because this is how we're wiring it up. Down here below, once we go down to the dip switch pins, the first pin on the dip switch, the second pin on the dip switch, and the third pin on the dip switch, and we're wiring it to pin 2, 3, and 4, respectively. You'll notice that this is very, very much the same. We've just added this here for the extra 2 switches, and we've added these here too for the extra 2 lights. You'll notice the same is going down for the most of the code below. In the setup, we simply say that the cabin lights are going to be an output, the storage lights are going to be an output, and now the cockpit lights are also going to be an output. We just added 2 more outputs down here. And then we have the following. We have cabin lights is going to be the input on the dip switch, and then we just added the simple storage light, and cockpit lights is going to be the additional inputs for the extra 2 pins that we're going to be wiring up today. If you go down to void loop, you'll notice that we have, remember, the exact same code as yesterday, but instead of written once, it's written 3 times. So if the first switch is in the on position, then we want to turn that corresponding light on, else we want to keep it off. Same exact scenario for the second pin, and same exact scenario for the third pin. And with that, we have the finished code for day 4, simply taking what we did yesterday and writing it a couple extra times for the extra pins. And that's about it.
Welcome to the wiring example video for day 4. Today we'll be expanding on what we built on day 3, using mostly the same ideas, but increasing our capability to be able to handle 3 independent lighting circuits. Since we are pretty closely repeating what we did last time, there's not a lot that is new to explain. As before, our breadboard contains 2 separate circuit areas that are used to handle on the left-hand side the hero input and on the right-hand side the LED output functions. The difference here being that now each of these 2 areas now includes 3 separate channels rather than just 1. We can see that on the input side, here on the left, we are now using all 3 channels of the dip switch module. We also now have a common 5-volt bus that is being used along the lower red line here. It's being used to supply 5 volts to each of the 3 channels of the dip switch. Each of those channels feeds through to its respective 10 kilo ohm limit resistor here before each of those resistors then connects to a common ground bus supplied by this black wire from the Hero. Each of those 3 channels, in addition to feeding through the 10 kilo ohm resistor, connects with a separate wire to each of the input pins on the Hero. So now we have 3 of these signal wires, a brown wire, a white wire, and a yellow wire, which in turn connect to pins 2, 3, and 4, as those are the pins specified as input in our software sketch. Switching over to the output side, we now have 3 output LEDs, a red, a blue, and a green, and those will be controlled by our 3 switches 1, 2, and 3. Each LED is connected on its low side to this common ground bus that we provided and we're using on the input side. We can see that there are 3 black jumper wires connected from ground to the low side of our 3 LEDs. Finally, our red, blue, and green LEDs are connected to each of the 3 output pins on the Hero. So we have an orange wire connected here to the red LED. We have a blue wire connected on its positive side, on the positive side of the LED, also to the Hero, and finally a green wire. And those are connected to pins 10, 11, and 12, also consistent with what's in our software sketch. So that pretty much completes our setup for the day 3 circuit. So let's go ahead and upload the sketch and try it out. So we'll load the sketch. And now that the sketch is loaded, it should be running. We have all of the switches in the off position right now, so we wouldn't expect to see anything. So we'll go ahead and we'll put switch 1 into the on position. And sure enough, just as we'd expected from day 3, the red LED comes on. But now I can have any combination of the 3 switches on or off. So for example, I could put switch 3 into on and get green to come on. Or I can have all 3 of them on together, or I can turn number 1 off, and so on. So as you play around with this, you'll be able to confirm that the logic in our software sketch and the wiring that we've put together here with the Hero and our breadboard agree with one another and have the desired functionality. So that's all for today's exploration. Next, after we take a day off for our creative activity, we'll be returning on day 6 to introduce a new type of sensor component into our repertoire. And so we'll see you then.
Ah, you're back. That was barely enough time to even begin missing you. Well, congratulations, dear explorer, on surviving the first week of your unanticipated yet thoroughly avoidable sea adventure. You've turned this sunken wreck from a murky cave into a well-lit tin can. You're proving quite resourceful for an oxygen breather. Bravo! Or whatever it is your kind says. Now that you have your lights, it seems that I can see into your storage bay with newfound clarity. My sensors are picking up a solar array that was previously hidden in the murkiness. I must admit, I didn't notice it earlier, but then again, it was darker than the depths of a supermassive black hole in there. Let's hold on to that glimmer of hope. The hydroponic system is getting up to speed, and I've altered the resistances on the new lights, so wiring up an LED doesn't turn this ship into the largest underwater fireball in history. Rest up, explorer. You've done some great work, and it looks like we're out of immediate danger.